So in this video, we are going to talk about plotting some of our filters. Now, we can do this using the filter coefficients that we've already generated, and this video will also kind of inherently talk about some implementation details of filters. So in, I believe, our first video, we talked about generating these 6 filter coefficients, B0, B1, B2, A0, A1, and A2, and you can see that I have them all as inlets here to this particular block. So you can take for granted that I'm referencing this whole patch in another block above it, and I'm feeding it those 6 inlets. And you see over here, this is really where the magic happens. So we have a transfer function. I've said it a million times. Those are transfer function coefficients. Well, this is what that really means. And what's important here is that we are essentially creating a function that directly plots the shape of the filter based on the transfer function coefficients. Now, at first I tried plotting the filter by just taking some noise, filtering it, and then plotting the shape of the output, which means taking an FFT of the noise after it's been filtered, and that just didn't work very well for a number of reasons. I won't go into that. So what we're doing here instead is using the transfer function coefficients directly to filter to plot the filter, excuse me. So now the most operative part of this function is z. And I'll write now here that z equals to e to the power of j omega. And if you've ever seen exp is usually how in a programming language how we use e, and the argument to exp is the power that e is raised to. So omega is our frequency vector, and so again, perhaps it's important to note that omega is equal to 2 times pi times f. So if I wanted to evaluate the magnitude of the transfer function at just a single frequency, let's say 100 hertz, I could use omega as 2 times pi times 100, which means z would become e to the power of j times 2 times pi times 100, and then I would plug this z in to these 4 places here, z here and here, and z squared here and here. But we want to evaluate the transfer function at a range of frequencies. And so what I've done is I've stored in some text files the value for z at a bunch of different points. And in order to have our plot essentially have the shape that is most common, which is a log shape, I've stored points of z that are themselves log spaced. Now, I don't think there is a way within PureData to actually display a log spaced frequency axis. And most commonly, when you look at a magnitude plot, you're seeing linearly spaced x points that are displayed on a logarithmic axis. And that's because when you take an FFT, the points you get in frequency are linearly spaced, and so you log space your x-axis in order to look at them in a way that makes more sense. We're doing the opposite. We can only plot our x-axis, our frequency axis in this case, linearly, and so if we use log-spaced points, then we'll get the kind of shape that we desire. So I've stored 100 values of the real part of z, the imaginary part of z, the real part of z squared, and the imaginary part of z squared. And those are all here. So this is z1, meaning z to the power of 1, the real part, z squared, the real part, z to the power of 1, the imaginary part, z squared, the imaginary part. And those all are here. This is a great way to kind of store long vectors external to PD and then reference them. So if I kind of hit this, it'll bang it and load it in. You can see in these plots, obviously, they're stored in text files, they're not changing. So these are the 4 arrays that I'm referencing, and of course, we can't explicitly deal in imaginary and real parts in PureData, as we discussed in a previous video. So we kind of have them threaded separately, and then we'll eventually take the magnitude and put them together. And that's what we're doing here with these square root. You can see that we're squaring something here, adding them together, and then taking the square root. So, for reference, the magnitude of real and imaginary parts also the absolute value equals to square root of the real part squared plus the imaginary part squared. So we did that in a previous video, but I'll write that out explicitly here. So yeah, we're exploiting all these things to just plot the shape of the filter based on this transfer function. So we have the real part of z coming in here, and it's getting multiplied by b1, as it should. The function says so right here, multiply z by b1. And then you can also trace it's coming down, it's getting multiplied by a1, again, as it should. And so same thing for z squared, multiplied by b2, and z squared is also getting multiplied by a2. Now, we have to multiply both the real and imaginary parts by the corresponding transfer function coefficients. So you'll see that b2 is not b1 is not only multiplying z1, b1 is also multiplying the imaginary part of z1. And we have these kind of two separate trees. This is kind of the left side is where the real part takes place, and the right side is where the imaginary part takes place. B naught and A naught only show up in their respective, the real part of the respective trees, because the coefficients themselves here are purely real. And therefore, they only need to be added to the real part of the tree. So B naught is purely real, A naught is purely real. We only handle that on the left side and on this other left side. And then, like I just explained, we kind of square each side. Happened here, the same thing, taking up two inlets of a multiplication block makes it squared, adding them together and taking them the square root, as is the magnitude defined by this equation. So this is the numerator. The B vector makes up our numerator. It's on the left inlet of this divide block. The A vector takes up our denominator, the right inlet of this divide block, and then we're taking the magnitude in decibels, which again is actually a way of log spacing our y-axis as well. So we are passing the division of the numerator by the denominator to log 10 and then multiplying by 20. And that's 20 times log 10 of the linear magnitude of our transfer function is the way we most commonly evaluate the magnitude in decibels of our transfer functions. And that's really it. There are some more kind of PureData implementation details that need to be gone over here, but before I do that really quickly, let me just show you that it works. I'm going to go up one level to those. Now I'm in the patch. I know you can't see it in the video here, but I'm in the patch that is controlling the transfer function coefficients, and I'm changing the filter cutoff in Q. So you can see that this runs in real time. Now, on that note, getting it to run in real time, it's a little tricky. There are some problems, and I'll link a good PureData forum thread in the description that kind of talk about the like the timing of certain blocks and why it essentially needs to be done this way. I was originally using vline, and when I would bang vline manually, I would kind of have the same bang was set up here, and I had vline here instead of line, and I had a slightly different message here. And that worked fine, but when I hooked a metronome block up to vline, it did not work properly. So I've used line instead, and I've set the block size to 1. So traditionally, PureData is working in terms of frames, 64 samples per frame. I've essentially set it up to work on a sample by sample basis by saying each block is only a single sample. And what we're doing with line here is we're creating a ramp that just sweeps through all the indexes of these vectors. So it's going from 0 to 100, and it's doing so in 2.676 milliseconds. And actually, I believe this should be 99 because it starts at index 0. So the might make a small difference there. So right, there are 100 indexes, which mean the indexes themselves are really 0 through 99. So it should go from 0 to 99 in this amount of time. And we then need to set it back to 0 so we can start that whole process over again. So this takes 2-point-something milliseconds, and then I have this delayed by 3 milliseconds. So, by the time this is done, then it gets this bang that was delayed and sets it back to 0 so it can do the whole thing over again. And yeah, that's essentially that. This line argument creates that just linear ramp that reads all these coefficients out in order, and they all propagate through, get multiplied and divided as they need to be, and then eventually written into the filt plot vector. So yeah, that's that. I now have this filt plot incorporated into my other filter block, which we've seen in previous videos. So now we can see the time domain waveform at the output of the filter, as well as the filter shape in frequency space.